Hello and welcome. So, today we will discuss the structure of diamond. We have discussed various forms of carbon like graphite we have already discussed. So, today let us look at what is the structure of diamond, which is also a form of carbon. So, diamond basically has the diamond cubic crystal structure. So, this diamond cubic structure, let me try to draw the unit cell of the diamond cubic structure for you. So, let us begin with the cube. It is a cubic crystal, so it has a cubic unit cell. So, I am beginning with the cube. So, this is a skeleton cube and will become diamond cubic when we populate it with properly located atoms. So, let us place the carbon atoms now. We place the carbon atoms at all the corners of the unit cell. So, that is the 8 atoms at the corners. It is a face centered cubic unit cell. So, we place atoms at face centers also. So, top and bottom face center and left and right face center, we need to place the front and back also. Front face center and the back face center. So, we have got for 6 more atoms. So, 8 at the corner, 6 at the face centers. At the moment it will be a face centered cubic crystal, but diamond cubic crystal is not a face centered cubic crystal. It has additional atoms and we place those additional atoms at the body diagonals. Those additional atoms are located at the body diagonals. So, let us identify the body diagonals. So, one body diagonal is emerging from here, and on each of the body diagonal the atom is either at 1/4 or 3/4 location. So, starting with this, with this corner I have drawn a body diagonal and I have located an atom at 1/4 of the total length of the body diagonal. Then I go from this at this corner, from this corner another body diagonal emerges. On that body diagonal I place an atom which is 3/4 from the bottom. So, it is now 1/4 from the top. So, it comes somewhere there. Then cyclically I go to the third body diagonal here. So, I started with this body diagonal, placed 1/4, then this next body diagonal I placed 3/4, the third body diagonal I again place 1/4. Atom, and the final fourth and the last body diagonal. On this body diagonal, I am sorry, my diagonal this time has become a little more curved, but anyway. So, I place another 1/4 one there. So, the whole thing also has 4 additional atoms. So, diamond cubic crystal structure has all the atoms for a face centered cubic crystal plus 4 additional atoms, one sitting on each of the 4 body diagonals. And the way it sits, I have already shown you that on one body diagonal it is at 1/4, then on an adjoining body diagonal, starting from an adjoining atom at the base adjoining corner of the square base. So, there it is at 3/4, then again 1/4 and then again 3/4. So, alternately it goes 1/4 and 3/4 location. I am sorry, I have made a mistake here. So, let me cross this out. So, 1/4 on the first diagonal, 3/4 on the second diagonal, then 1/4 on the third diagonal, and again this one I have placed 1/4, it should have been on the 3/4 location. So, that comes there. Now, it is okay. So, the whole appearance looks a little complicated. So, sometimes a little bit a better clarity comes if we draw it in the projection. So, let us try to draw the unit cell in the projection. So, we will project the unit cell on the xy plane, on the base plane. So, let us try to draw that. So, the base plane of course is a square. So, I draw a square. This is my x axis, this is my y axis. Now, this is a 2-dimensional projection. So, z axis is not shown, z axis is perpendicular to my projection plane. So, this is the square. If we label it, let us say, let me try to label this as A, B, C, D. So, the base of the unit cell A, B, C, D is what you are seeing here as this is square. Now, you can see that this square itself is populated with atoms. So, all those atoms we place. So, atoms are at the corners, and atom is at the face center. So, these atoms are as they are in the original unit cell. Other atoms are not on the base plane, they are above the base plane, and we will project them onto this base plane. So, for example, let us look at this face center, this one here. So, if I project it vertically downward, it will come exactly on the middle of the AB edge. So, on the middle of the AB edge, I have another atom projected, which is representing the atom which in the original unit cell was the center of the left face. So, the left face center got projected here. Similarly, the front face center will get projected in the middle of this edge, the right face center will get projected there, and the back face center will get projected there. So, we have projected all the vertical face center, and we already have the atoms on the base plane. The top, now only atoms left are those which are on the body diagonals and on the top face. The top face atoms, when you will project, will coincide exactly with the corners and the face center of the bottom face. So, no new locations are generated by that. So, we leave that out. Now, let us look at the body diagonal one. So, this particular atom, this particular body diagonal one, which is located at 1/4 of this body diagonal is starting from A. So, what is its coordinates? So, since it is 1/4 of the body diagonal, and a body diagonal direction, if you find the Miller indices, is a 1 1 1 direction. So, it is equally inclined to all the 3 axes. So, along this all the 3 coordinates are equal, and since it is 1/4 of the entire body diagonal, the coordinate of this particular atom is 1/4 along x, 1/4 along y, and 1/4 along z. So, when I will project this, it will show 1/4 along x and 1/4 along y, and z component of course will not be seen in the projection. So, if I now project this particular green atom on the body diagonal, I will get at 1/4, 1/4 and here. Similarly, if I project this one, this particular one will come here, the third one will go there and fourth one will go there. So, this completes the projection, but the standard crystallographic projection, the convention is to show the z fractional coordinate, the z fractional z component, because x y component can easily be read. So, I know for this atom, because it is 1/4 of this side and 1/4 of this side, its x and y coordinate is 1/4, 1/4. But since it is projected, I do not know the z coordinate. So, the z coordinate can be explicitly written on the projection itself. So, let us do that. Let us write the z coordinate of all the atoms. So, these A, B, C, D of course, were on the plane itself. So, their z component were 0. So, I write 0 for them. The one on the vertical face center, this one was to, half of the total height of the unit cell. So, I write half to indicate that it is at half height, half the height of the unit cells. So, these 4 atoms, the front face center, the right face center and the back face center, all these are at half height. And then the 4 on the body diagonal, you saw that this one was 1/4, 1/4, 1/4. So, its z component was 1/4. So, I write 1/4 to indicate that the height above the projection plane is 1/4. Similarly, this one, which is this here, is 1/4. And the other two on this diagonal, since you have an atom at 3/4 distance, its height from the basal plane also is 3/4. So, I write 3/4, 3/4. So, this completes the projection, and so sometimes you can see this also gives you the 3-dimensional view, this gives a 2-dimensional projection, but sometimes it is clearer to see things in the projection, and sometimes it is better to use this isometric view. So, you can use whatever way you like. Both are giving you exactly the same information, that the diamond cubic unit cell is a cubic unit cell with atoms at the corners and the atoms at the face centers and 4 atoms located appropriately, one each on the 4 body diagonals. So, that completes the description of the unit cell. However, we have described all crystal structure, we have seen this, and this has been our theme. We have done this for graphite also, that all crystal structure should be described as a combination of lattice and motif. So, we have drawn the unit cell, but what is its lattice and what is its motif? So, let us try to look at that. We already know that face centered cubic is a lattice. So, which means that the face centered cubic unit cell, all the black atoms which are located at the face centered cubic, all are equivalent in the lattice sense. So, they are forming a lattice, there is no problem. However, the additional 4 atoms, whether they are at lattice points or not, is what we have to check. So, let us go in this direction. Let us start with this as my lattice point, one lattice point, say 1, and from this I go along the body diagonal and I find this green atom, and I travel a distance 1/4 along the body diagonal. So, 1 has a neighbor, and let me call this atom 2. So, 1 has a neighbor 2 in this body diagonal direction at this distance. If I travel the same distance from 2, that is, if I travel another 1/4 distance along the body diagonal, then I would have traveled half the distance of body diagonal, half the length of body diagonal, and I will end up in the center of the cube. But please note that we have not placed any atom at the center of the cube. So, which means the green atom does not have a neighbor in the same direction at the same location as the black atom, which clearly shows that if one is the lattice point, one is considered as a lattice point, 2 cannot be considered as a lattice point. So, what we have to do is to associate 2 to the lattice point. So, our motif should at least be 2 atoms, 2 has to be associated to the lattice point at 1. So, let us propose or consider this as our possible motif. Now, if since each lattice points are equivalent, each motif also has to be equivalent, and if we have given a motif atom to this lattice point, similar motif atom should be there for all the lattice points. So, let us consider this face center one. So, from here we went 1/4 along x, 1/4 along y and 1/4 along z to find the motif atom. From here if we start, we are already at the face center. So, we will go 1/4 along this, 1/4 along y and then 1/4 z. So, exactly we will come to the location of this atom at the other body diagonal. So, we can see that the motif is actually repeated at this atom at the face center also. Similarly, if you look at this vertical face center, from here if you go 1/4 along x, 1/4 along y and 1/4 along z, you will come to this atom which is sitting at 3/4. Recall that this center atom is already at half height. So, if you go further half 1/4 height up, you will come to 3/4 and this atom was the 3/4 atom. So, this is also associated with this, and this one is associated with the back face center. So, easier to see probably in the projection that this 1/4 atom is associated with that lattice point, this 1/4 3/4 atom is associated with this face center at the back, this 3/4 is associated with the face center at the left, and this 1/4 is associated with the face center at the bottom. So, now we are finding that we have accounted for all the extra 4 atoms, all of them are associated with their corresponding lattice point. So, we do not need any more. So, the motif is 2 atom motif. So, we can write the diamond cubic structure. So, the conclusion of this analysis is that diamond cubic, briefly we can write DC, diamond cubic crystal, so recall that lattice is only, the green atoms are not contributing to the lattice. So, lattice is only defined by the black atoms. So, the lattice is face centered cubic, it is FCC lattice plus of course, it has to have motif, and we have seen that motif has 2 atoms, one black and one green. Now, how do I give the coordinates of the motif atom? So, remember the coordinates of the motif atom is given as displacement coordinates with respect to the lattice point. So, the black atom is sitting at the lattice point. So, it is not displaced. So, its coordinate is O. The green atom is displaced with respect to the lattice point, as you have already seen now by translations 1/4 along x, 1/4 along y and 1/4 along z. So, the second atom in the motif is given coordinate 1/4, 1/4, 1/4. So, we have successfully analyzed the diamond cubic crystal as a lattice plus motif. The crystal structure is diamond cubic, lattice is FCC lattice, but unlike we saw FCC crystal also, cubic close packed crystal. Contrast this with cubic close packed structure CCP, which we have already seen, which also had FCC lattice, but it had only one atom motif, only one atoms were sitting only at the lattice point. In diamond cubic, since additional atoms are sitting beyond lattice point, we get a motif of two atoms, one at the lattice point and one displaced by this vector 1/4, 1/4, 1/4 with respect to the lattice point. So, an interesting question comes, and it is a widespread confusion in literature as well as on the web, is there anything called diamond cubic lattice? So, we have already seen the crystal of diamond is a diamond cubic crystal. So, it is not diamond cubic lattice, but diamond cubic crystal. And when we analyzed it, we found that the lattice was FCC lattice. So, there is no lattice called diamond cubic lattice, but diamond cubic is a crystal having FCC lattice with a motif of two atom at O and quarter quarter quarter. So, diamond cubic lattice is a wrong phrase and should not be used. I trust that after this video you will not be using this incorrect phrase diamond cubic lattice, which is quite common on the internet. I think if you search, if you do an exact phrase search, please do this exercise, do an exact phrase search diamond cubic lattice on Google. And it will happily throw you thousands of websites which will be using phrase diamond cubic lattice, which is incorrect. So, do this on the Google. You can also see why this is incorrect. We have already met 14 Bravais lattices. So, out of those 14 Bravais lattices, there are only 3 cubic lattices, and they are simple cubic. You may recall that the 3 cubic lattices are cubic P, simple cubic, cubic F, face centered cubic, and cubic I, the body centered cubic. So, there is no such diamond cubic lattice. If you introduce a phrase like diamond cubic lattice, that means you are talking of 15th Bravais lattice, which is an incorrect terminology. So, never use diamond cubic lattice. If you are using diamond cubic adjective, should be used only for crystal and not for the lattice. So, diamond cubic crystal having an FCC lattice. We also know, we have from our previous studies, that there is a tetrahedral bonding of carbon. Each carbon atom is bonded to 4 other carbon atoms located on the corners of a tetrahedron in diamond. So, if I take a carbon atom in diamond, it is supposed to be bonded to 4 other carbon atoms and these 4 carbon atoms, if I join, they are on the vertices of a tetrahedron. They are forming a tetrahedron. So, where is this tetrahedron in our unit cell? So, this was something which was not obvious. So, I want in this slide, I want to show you where is this tetrahedron in the diamond cubic structure, diamond cubic crystal structure. So, let us look at this 3-dimensional picture of the unit cell first, and we see that every corner in an FCC structure, we have already seen in the cubic close packed case that you have tetrahedral and octahedral void. So, a tetrahedron is formed by any corner atom. If you look at this corner atom, let us say this one, and at each corner 3 faces meet, and if you look at, so at this corner, left face, back face and the bottom face is meeting. Consider the face centers of all these 3 faces which are meeting. So, now you have 4 atoms, the corner one and the 3 face center. You can show, you have shown already in when we were studying the cubic closed packed structure, that these 4 atoms form a tetrahedron. They form a nice tetrahedron. And then this 1/4, 1/4, 1/4 atom on the body diagonal, you can show is exactly the centroid of this tetrahedron. So, this is where this green atom, the one sitting on the body diagonal, then forms a tetrahedral bonding with all the 4 neighboring carbon atom. So, the red lines which I have drawn are not carbon carbon bonds, they are the reference lines to show the tetrahedron, and the blue lines here are the actual carbon carbon bonds. So, I have done this for this 1/4 atom in this unit cell. If you do this for other atoms, you will find that each atom is at the center of a tetrahedron. So, this is what makes the 3 dimensional diamond structure, and I have a model here to show you. So, this carbon atom is at the center of 4 atoms. It is bonded to 4 atoms. So, you can see one atom there, one atom here, one down there and another down there. Of course, it is not easy, I can see it is not easy to see on a video like this. You have to have a model to play with, but then such a structure will continue. And if I just separate my model to show you, just one tetrahedral unit I am trying to separate now from my 3 dimensional structure. So, that looks like this. So, this is probably easier to see. You can see the 4 atoms, one the central one connected with 4. So, and so you can model it with the tetrahedron. Here is the tetrahedron solid. So, if I place it like this, so you can see that there is a base of 3. So, and these lines are the edges of the tetrahedron. These lines are here like this, and they are not the or like this. So, this edge, this bottom edge is actually not a bond, but that is the edge of the tetrahedron. So, if I place it like this, so that is the edge of the tetrahedron. So, tetrahedron can be seen, you can see the tetrahedron can be seen in 2 ways. One is this standard way, in which case there is a base of 3 atoms and one atom is sitting on the top of that base. So, the vertical axis in this case is a 3-fold axis. If I look at this axis, that is a 3-fold axis. Whereas, the other way of looking at the tetrahedron is to stand it on an edge. If you stand it on an edge, then you see you have 2 bottom atoms, which I am now holding by my hand, and there are 2 atoms on the top, and the orientation of the line of these atoms, the bottom is oriented one way and this is oriented orthogonal to the bottom atoms. So, the 2 lines are at 90° to each other. So, this is another way of looking at tetrahedron. In this case, the vertical vertical axis is a two-fold axis. So, you can orient the tetrahedron either as with three-fold vertical, or you can orient the tetrahedron with a two-fold vertical in this way. So, in the projection, if you try to find the tetrahedron, so you can see this was the 1/4 atom, and there are 4 atoms here. So, this one was, let me write the coordinates, half, half, this one was 0, 0, and this particular one was the 1/4. So, you can see that there are 2 atoms below 0, 0, then 2 atoms above half, half in my this tetrahedron orientation, 2 atoms below and 2 atoms above, and they are at 90 degree, they are at 90 degrees. So, that is what is forming a tetrahedron. So, these 4 atoms, the black atoms are forming the tetrahedron, and this 1/4 atom is at the centroid of the tetrahedron. So, in this case, if I outline in red, the tetrahedron is shown here. The projected tetrahedron will look like a square like this with the green atom in the center. So, we have seen how the tetrahedral bonding of diamond fits in the unit cell, and we have also seen how the diamond structure, the diamond cubic crystal structure can be analyzed or discussed in terms of lattice and motif, and we have emphasized that there is nothing like diamond cubic lattice, there is only diamond cubic crystal which has an FCC lattice, and there are 2 atom motif. So, with this we end the video.